Graphene is pure carbon in the form of a very thin, nearly transparent sheet, 1 atom thick. It is remarkably strong for its very low weight and it conducts heat and electricity with great efficiency. While scientists had theorized about graphene for decades, it was first produced in the lab in 2004. Because it is virtually two-dimensional, it interacts oddly with light and with other materials. Researchers have identified the bipolar transistor effect, ballistic transport of charges and large quantum oscillations. Technically, graphene is a crystalline allotrope of carbon with two-dimensional properties. In graphene, carbon atoms are densely packed in a regular sp2 bonded atomic scale chicken wire pattern. Graphene can be described as a 1-atom thick layer of graphite. It is the basic structural element of other allotropes, including graphite, charcoal, carbon nanotubes and fullerenes. It can also be considered as an indefinitely large aromatic molecule, the limiting case of the family of flat polycyclic aromatic hydrocarbons. Graphene research has expanded quickly since the substance was first isolated in 2004. Research was informed by theoretical descriptions of graphene's composition, structure and properties, which had all been calculated decades earlier. High-quality graphene also proved to be surprisingly easy to isolate, making more research possible. Andrei Geim and Konstantin Novoselov at the University of Manchester won the Nobel Prize in Physics in 2010 for groundbreaking experiments regarding the two-dimensional material graphene. Definition: graphene is a combination of graphite and the suffix -ene, named by Hans Peter Bohrheim, who described single-layer carbon foils in 1962. The term graphene first appeared in 1987 to describe single sheets of graphite as a constituent of graphite intercalation compounds. Conceptually, a GIC is a crystalline salt of the intercalant and graphene. The term was also used in early descriptions of carbon nanotubes, as well as for epitaxial graphene and polycyclic aromatic hydrocarbons. The IUPAC Compendium of Technology states, previously, descriptions such as graphite layers, carbon layers, or carbon sheets have been used for the term graphene. It is incorrect to use for a single layer a term which includes the term graphite, which would imply a three-dimensional structure. The term graphene should be used only when the reactions, structural relations or other properties of individual layers are discussed. Geim defined isolated or freestanding graphene as a single atomic plane of graphite, virtually Euro, and this is essentially a Euro is sufficiently isolated from its environment to be considered freestanding. This definition is narrower than the IUPAC definition and refers to cleaved, transferred and suspended graphene. Other forms of graphene, such as graphene grown on various metals, can become freestanding if, for example, suspended or transferred to silicon dioxide, CO2, or silicon carbide. Graphene can be considered an infinite alternate polycyclic aromatic hydrocarbon. History: in 1859 Benjamin Collins Brodie was aware of the highly lamellar structure of thermally reduced graphite oxide. The structure of graphite was solved in 1916 by the related method of powder diffraction. It was studied in detail by V. Köhler 1/4 TTER and P. Haney in 1918, who also described the properties of graphite oxide paper. Its structure was determined from single crystal diffraction in 1924. The theory of graphene was first explored by Pierre Wallis in 1947 as a starting point for understanding the electronic properties of 3D graphite. The emergent massless Dirac equation was first pointed out by Gordon Walter Semnoff and David P. DiVincenzo and Eugene J. Meal. Semnoff emphasized the occurrence in a magnetic field of an electronic Landau level precisely at the Dirac point. This level is responsible for the anomalous integer quantum Hall effect. The earliest TEM images of fullerene graphite were published by G. Ruess and F. Vogt in 1948. Later, single graphene layers were also observed directly by electron microscopy. Before 2004 intercalated graphite compounds were studied under a transmission electron microscope. Researchers occasionally observed thin graphitic flakes and possibly even individual layers. An early, detailed study on fullerene graphite dates to 1962. Starting in the 1970s, single layers of graphite were grown epitaxially on top of other materials. This epitaxial graphene consists of a single atom-thick hexagonal lattice of sp2 bonded carbon atoms, as in freestanding graphene. However, there is significant charge transfer from the substrate to the epitaxial graphene, and, in some cases, hybridization between the d orbitals of the substrate atoms and I orbitals of graphene, which significantly alters the electronic structure of epitaxial graphene. Single layers of graphite were also observed by transmission electron microscopy within bulk materials, in particular inside soot obtained by chemical exfoliation. Efforts to make thin films of graphite by mechanical exfoliation started in 1990, but nothing thinner than 50 to 100 layers was produced before 2004. Initial attempts to make atomically thin graphitic films employed exfoliation techniques similar to the drawing method. Multi-layer samples down to 10 nm in thickness were obtained. Old papers were unearthed in which researchers tried to isolate graphene starting with intercalated compounds. These papers reported the observation of very thin graphitic fragments by transmission electron microscopy. Neither of the earlier observations was sufficient to spark the graphene gold rush, which awaited macroscopic samples of extracted atomic planes. One of the very first patents pertaining to the production of graphene was filed in October 2002. Titled, Nanoscaled Graphene Plates, this patent detailed one of the very first large-scale graphene production processes. 2 years later, in 2004, André Geim and Kostya Novoselov at University of Manchester extracted single-atom-thick crystallites from bulk graphite. They pulled graphene layers from graphite and transferred them onto thin CO2 on a silicon wafer in a process called either micromechanical cleavage or the Scotch tape technique. The CO2 electrically isolated the graphene and weakly interacted with it, providing nearly charge-neutral graphene layers. The silicon beneath the CO2 could be used as a backgate electrode to vary the charge density in the graphene over a wide range. They may not have been the first to use this technique. US 6,667,100 filed in 2002, describes how to process commercially available flexible expanded graphite to achieve a graphite thickness of 0.01 thousandth of an inch. The key to success was high-throughput visual recognition of graphene on a properly chosen substrate, which provides a small but noticeable optical contrast. The cleavage technique led directly to the first observation of the anomalous quantum Hall effect in graphene, which provided direct evidence of graphene's theoretically predicted Beres phase of massless Dirac fermions. The effect was reported soon after by Philip Kim and Yuanbo Zhang in 2005. These experiments started after the researchers observed colleagues who were looking for the quantum Hall effect in Dirac fermions in bulk graphite. Even though graphene on nickel and on silicon carbide have both existed in the laboratory for decades, graphene mechanically exfoliated on CO2 provided the first proof of the Dirac fermion nature of electrons. Geim and Novoselov received several awards for their pioneering research on graphene, notably the 2010 Nobel Prize in Physics. Properties, structure. Graphene stability is due to a tightly packed, periodic array of carbon atoms and an sp2 orbital hybridization, a combination of orbitals px and py that constitute the I-fluorine bond. Graphene has 3 I-fluorine bonds and 1 I-euro bond. The final pz electron makes up the I-euro bond, and is key to the half-filled band that permits removing electrons. Graphene sheets in solid form usually show evidence in diffraction for graphite's layering. This is true of some single-walled nanostructures. However, unlayered graphene with only rings has been found in the core of pre-solar graphite onions. TEM studies show faceting at defects in flat graphene sheets and suggest a role for two-dimensional crystallization from a melt. Graphene can self-repair holes in its sheets, when exposed to molecules containing carbon, such as hydrocarbons. Bombarded with pure carbon atoms, the atoms perfectly align into hexagons, completely filling the holes. The atomic structure of isolated, single-layer graphene was studied by transmission electron microscopy on sheets of graphene suspended between bars of a metallic grid. electron diffraction patterns showed the expected honeycomb lattice. Suspended graphene also showed rippling of the flat sheet, with amplitude of about 1 nanometer. These ripples may be intrinsic to the material as a result of the instability of two-dimensional crystals, or may originate from the ubiquitous dirt seen in all TEM images of graphene. Atomic resolution real space images of isolated, single-layer graphene on CO2 substrates are available via scanning tunneling microscopy. Photoresist residue, which must be removed to obtain atomic resolution images, may be the adsorbates observed in TEM images, and may explain the observed rippling. Rippling on CO2 is caused by conformation of graphene to the underlying CO2, and is not intrinsic. Chemical: graphene is the only form of carbon in which each single atom is in exposure for chemical reaction from two sides. It is known that carbon atoms at the edge of graphene sheets have special chemical reactivity, and graphene has the highest ratio of edgy carbons. In addition, various types of defects within the sheet, which are very common, increase the chemical reactivity. The onset temperature of reaction between the basal plane of single-layer graphene and oxygen gas is below 260 AA°C, and the graphene burns at very low temperature. In fact, graphene is chemically the most reactive form of carbon, owing to the lateral availability of carbon atoms. Graphene is commonly modified with oxygen and nitrogen containing functional groups and analyzed by infrared spectroscopy and X-ray photoelectron spectroscopy. However, determination of structures of graphene with oxygen and nitrogen containing functional groups is a difficult task unless the structures are well controlled. In 2013, Stanford University physicists reported that sheets of graphene 1 atom thick are 100 times more chemically reactive than thicker sheets. Electronic: graphene is a semi-metal or zero-gap semiconductor. 4 electronic properties separate it from other condensed matter systems. Electronic spectrum: electrons propagating through graphene's honeycomb lattice effectively lose their mass, producing quasi-particles that are described by a 2D analog of the Dirac equation rather than the Schur-Paragraph-Dingo equation for spin 1 or 2 particles. Dispersion relation: using a conventional tight binding model, the dispersion relation produces energy of the electrons with wave vector k's. With the nearest neighbor hopping energy I cubed 0 per mol 2.8 eV and the lattice constant AA per mol 2.46 AA. The conduction and valence bands, respectively, correspond to the different signs. They touch each other at 6 points, the K values of the two-dimensional hexagonal Brillouin zone. 2 of these 6 points are independent, while the rest are equivalent by symmetry. In the vicinity of the K points the energy depends linearly on the wave vector, similar to a relativistic particle. Since an elementary cell of the lattice has a basis of 2 atoms, the wave function has an effective 2-spinor structure. As a consequence, at low energies, even neglecting the true spin, the electrons can be described by an equation that is formally equivalent to the massless Dirac equation. Hence, the electrons and holes are called Dirac fermions and the 6 corners are called the Dirac points. This pseudo-relativistic description is restricted to the chiral limit, that is, to vanishing rest mass MO, which leads to interesting additional features. Here VF106 AMS is the Fermi velocity in graphene, which replaces the velocity of light in the Dirac theory. Is the vector of the Pauli matrices, is the two-component wave function of the electrons, and E is their energy. The equation describing the electrons' linear dispersion relation is where the wave vector k is measured from the Dirac points. The equation uses a pseudospin matrix formula that describes 2 sublattices of the honeycomb lattice. Single-atom wave propagation: electron waves in graphene propagate within a single atom layer, making them sensitive to the proximity of other materials such as high dielectrics, superconductors and ferromagnetics. Electron transport: experimental results from transport measurements show that graphene has a remarkably high electron mobility at room temperature, with reported values in excess of 15,000 cm2 of R1 as R1. Additionally, the symmetry of the experimentally measured conductance indicates that hole and electron mobilities should be nearly the same. the mobility is nearly independent of temperature between 10 K and 100 K, which implies that the dominant scattering mechanism is defect scattering. Scattering by the acoustic phonons of graphene intrinsically limits room temperature mobility to 200,000 cm2 of R1 as R1 at a carrier density of 1012 ACMR2, which was later demonstrated and is greater than copper. The corresponding resistivity of the graphene sheet would be 10 AICM. This is less than the resistivity of silver, the lowest known at room temperature. However, for room temperature graphene on CO2 substrates, scattering of electrons by optical phonons of the substrate is a larger effect than scattering by graphene unregistered trademark S-own phonons. This limits mobility to 40,000 cm2 of R1 as R1. Electrical resistance in 40 nanometer wide nanoribbons of epitaxial graphene changes in discrete steps. The ribbon's conductance exceeds predictions by a factor of 10. The ribbons can act more like optical waveguides or quantum dots, allowing electrons to flow smoothly along the ribbon edges. In copper, resistance increases in proportion to length as electrons encounter impurities. Transport is dominated by two modes. One is ballistic and temperature independent, while the other is thermally activated. Ballistic electrons resemble those in cylindrical carbon nanotubes. At room temperature, resistance increases abruptly at a particular length or the ballistic mode at 16 micrometers and the other at 160 nanometers. The ribbons were grown on the edges of three-dimensional structures etched into silicon carbide wafers. When the wafers are heated to approximately 1000 degrees Celsius, silicon is preferentially driven off along the edges, forming nanoribbons whose structure is determined by the pattern of the three-dimensional surface. The nanoribbons had perfectly smooth edges, annealed by the fabrication process. Electron mobility measurements surpassing 1 million correspond to a sheet resistance of 1 ohm per square 2 orders of magnitude lower than in two-dimensional graphene. Graphene electrons can cover micrometer distances without scattering, even at room temperature. Despite zero carrier density near the Dirac points, graphene exhibits a minimum conductivity on the order of. The origin of this minimum conductivity is still unclear. However, rippling of the graphene sheet or ionized impurities in the CO2 substrate may lead to local puddles of carriers that allow conduction. Several theories suggest that the minimum conductivity should be. However, most measurements are of order or greater and depend on impurity concentration. Graphene doped with various gaseous species can be returned to an undoped state by gentle heating in vacuum. Even for dopant concentrations in excess of 1012 ACMR2 carrier mobility exhibits no observable change. Graphene doped with potassium in ultra-high vacuum at low temperature can reduce mobility 20-fold. The mobility reduction is reversible on heating the graphene to remove the potassium. Due to graphene's two dimensions, charge fractionalization is thought to occur. It may therefore be a suitable material for constructing quantum computers using anionic circuits. Anomalous quantum Hall effect. The quantum Hall effect is a quantum mechanical version of the Hall effect, which is the production of transverse conductivity in the presence of a magnetic field. The quantization of the Hall effect at integer multiples of the basic quantity it can usually be observed only in very clean silicon or gallium arsenide solids at temperatures around 3 K and very high magnetic fields. Graphene shows the quantum Hall effect with respect to conductivity quantization. The effect is anomalous in that the sequence of steps is shifted by 1/2 with respect to the standard sequence and with an additional factor of 4. Graphene's Hall conductivity is, where n is the Landau level and the double valley and double spin degeneracies give the factor of 4. These anomalies are present at room temperature, that is at roughly 20 degrees Celsius. This behavior is a direct result of graphene's massless Dirac electrons. In a magnetic field, their spectrum has a Landau level with energy precisely at the Dirac point. This level is a consequence of the Atiyah-Singer index theorem and is half-filled in neutral graphene, leading to the +1/2 in the Hall conductivity. Bilayer graphene also shows the quantum Hall effect, but with only one of the two anomalies. In the second anomaly, the first plateau at n equals 0 is absent, indicating that bilayer graphene stays metallic at the neutrality point. Unlike normal metals, graphene's longitudinal resistance shows maxima rather than minima for integral values of the Landau filling factor and measurements of the Shubnikova-de Haas oscillations, whereby the term integral quantum Hall effect. These oscillations show a phase shift of I-, known as Bilayer unregistered trademark S-phase. Bilayer unregistered trademark S-phase arises due to the zero effective carrier mass near the Dirac points. The temperature dependence of the oscillations reveals that the carriers have a non-zero cyclotron mass, despite their zero effective mass. Graphene samples prepared on nickel films, and on both the silicon face and carbon face of silicon carbide, show the anomalous effect directly in electrical measurements. Graphitic layers on the carbon face of silicon carbide show a clear Dirac spectrum in angle-resolved photoemission experiments, and the effect is observed in cyclotron resonance and tunneling experiments. Strong magnetic fields: in magnetic fields above 10 teslas or so, additional plateaus of the Hall conductivity at I fluorine Xi equals I1/2 E2 per hour with I1/2 equals 0, A plus or minus 1, A plus or minus 4 are observed. A plateau at I1/2 equals 3 and the fractional quantum Hall effect at I1/2 equals 1 or 3 were also reported. These observations with I1/2 equals 0, A plus or minus 1, A plus or minus 3, A plus or minus 4 indicate that the fourfold degeneracy of the Landau energy levels is partially or completely lifted. Casimir effect: the Casimir effect is an interaction between disjoint neutral bodies provoked by the fluctuations of the electrodynamical vacuum. Mathematically, it can be explained by considering the normal modes of electromagnetic fields, which explicitly depend on the boundary conditions on the interacting bodies' surfaces. Since graphene electromagnetic field interaction is strong for a one-atom thick material, the Casimir effect is of growing interest. Van der Waals force: the Van der Waals force is also unusual, obeying an inverse cubic, asymptotic power law in contrast to the usual inverse quartic. Massive electrons: graphene's unit cell has two identical carbon atoms and two zero-energy states, one in which the electron resides on atom A, the other in which the electron resides on atom B. Both states exist at exactly zero energy. However, if the two atoms in the unit cell are not identical, the situation changes. Hunt et al. Show that placing HBN in contact with graphene can alter the potential felt at atom A versus atom B enough that the electrons develop a mass and accompanying band gap of about 30 MeV. The mass can be positive or negative. An arrangement that slightly raises the energy of an electron on atom A relative to atom B gives it a positive mass, while an arrangement that raises the energy of atom B produces a negative electron mass. The two versions behave alike and are indistinguishable via optical spectroscopy. An electron traveling from a positive mass region to a negative mass region must cross an intermediate region where its mass once again becomes zero. This region is gapless and therefore metallic. Metallic modes bounding semiconducting regions of opposite sign mass is a hallmark of a topological phase and display much the same physics as topological insulators. If the mass in graphene can be controlled, electrons can be confined to massless regions by surrounding them with massive regions, allowing the patterning of quantum dots, wires, and other mesoscopic structures. It also produces one-dimensional conductors along the boundary. These wires would be protected against backscattering and could carry currents without dissipation. Optical. Graphene's unique optical properties produce an unexpectedly high opacity for an atomic monolayer in vacuum, absorbing I plus or minus a per mil 2.3% of white light, where I plus or minus is the fine structure constant. This is a consequence of the unusual low-energy electronic structure of monolayer graphene that features electron and hole conical bands meeting each other at the Dirac point, which is qualitatively different from more common quadratic massive bands. Based on the Slonczewski-Weiser-McClure band model of graphite, the interatomic distance, hopping value and frequency cancel when optical conductance is calculated using Fresnel equations in the thin film limit. Although confirmed experimentally, the measurement is not precise enough to improve on other techniques for determining the fine structure constant. Graphene's band gap can be tuned from 0 to 0.25 eV by applying voltage to a dual-gate Bilayer graphene field effect transistor at room temperature. The optical response of graphene nanoribbons is tunable into the terahertz regime by an applied magnetic field. Graphene oxide systems exhibit electrochromic behavior, allowing tuning of both linear and ultrafast optical properties. A graphene-based Bragg grating has been fabricated and demonstrated its capability for excitation of surface electromagnetic waves in the periodic structure by using 633 nm He laser as the light source. Saturable absorption. Such unique absorption could become saturated when the input optical intensity is above a threshold value. This nonlinear optical behavior is termed saturable absorption and the threshold value is called the saturation fluence. Graphene can be saturated readily under strong excitation over the visible to near-infrared region, due to the universal optical absorption and zero band gap. This has relevance for the mode locking of fiber lasers, where full-band mode locking has been achieved by graphene-based saturable absorber. Due to this special property, graphene has wide application in ultrafast photonics. Moreover, the optical response of graphene oxide layers can be tuned electrically. Saturable absorption in graphene could occur at the microwave and terahertz band, owing to its wide-band optical absorption property. The microwave saturable absorption in graphene demonstrates the possibility of graphene microwave and terahertz photonics devices, such as microwave saturable absorber, modulator, polarizer, microwave signal processing and broadband wireless access networks. Nonlinear Kerr effect. Under more intensive laser illumination, graphene could also possess a nonlinear phase shift due to the optical nonlinear Kerr effect. Based on a typical open and close aperture Z-scan measurement, graphene possesses a giant nonlinear Kerr coefficient of 10^7 SEM2 or Y1, almost 9 orders of magnitude larger than that of bulk dielectrics. This suggests that graphene may be a nonlinear Kerr medium, paving the way for graphene-based nonlinear Kerr photonics such as a soliton. Excitonic, first principle calculations with quasi-particle corrections and many body effects are performed to study the electronic and optical properties of graphene-based materials. The approach is described as 3 stages. With GW calculation, the properties of graphene-based materials are accurately investigated, including graphene nanoribbons, edge and surface functionalized armchair graphene nanoribbons, hydrogen-saturated armchair graphene nanoribbons, Josephson effect in graphene SNS junctions with single localized defect and scaling properties in armchair graphene nanoribbons. Thermal, graphene is a perfect thermal conductor. Its thermal conductivity was measured recently at room temperature and it is much higher than the value observed in all the other carbon structures as carbon nanotubes, graphite and diamond. The ballistic thermal conductance of graphene is isotropic, that is same in all directions. Graphite, the 3D version of graphene, shows a thermal conductivity about 5 times smaller. The phenomenon is governed by the presence of elastic waves propagating in the graphene lattice, called phonons. The study of thermal conductivity in graphene may have important implications in graphene-based electronic devices. Even on a substrate, thermal conductivity reaches 605,000 Wh/1. Stability. Ab initio calculations show that a graphene sheet is thermodynamically unstable if its size is less than about 20 nm and becomes the most stable fullerene only for molecules larger than 24,000 atoms. Conductivity. The near-room temperature thermal conductivity of graphene was measured to be between a 103 to a 103 Wh/1. These measurements, made by a non-contact optical technique, are in excess of those measured for carbon nanotubes or diamonds. The isotopic composition, the ratio of 12C to 13C, has a significant impact on thermal conductivity, where isotopically pure 12C graphene has higher conductivity than either a 50 to 50 isotope ratio or the naturally occurring 99:1 ratio. It can be shown by using the Wiedemann-Eurofranz law, that the thermal conduction is phonon-dominated. However, for a gated graphene strip, an applied gate bias causing a Fermi energy shift much larger than kBt can cause the electronic contribution to increase and dominate over the phonon contribution at low temperatures. The ballistic thermal conductance of graphene is isotropic. Potential for this high conductivity can be seen by considering graphite, a 3D version of graphene that has basal plane thermal conductivity of over a 1000 Ohm/1 In graphite, the C-axis thermal conductivity is over a factor of 100 smaller due to the weak binding forces between basal planes as well as the larger lattice spacing. In addition, the ballistic thermal conductance of graphene is shown to give the lower limit of the ballistic thermal conductances, per unit circumference, length of carbon nanotubes. Despite its 2D nature, graphene has 3 acoustic phonon modes. The 2 in-plane modes have a linear dispersion relation, whereas the out-of-plane mode has a quadratic dispersion relation. Due to this, the T2-dependent thermal conductivity contribution of the linear modes is dominated at low temperatures by the T1.5 contribution of the out-of-plane mode. Some graphene phonon bands display negative Gra1 coordinates parameters. At low temperatures the contribution from the negative Gra1 coordinates parameters will be dominant and thermal expansion coefficient negative. The lowest negative Gra1 coordinates parameters correspond to the lowest transversal acoustic ZA modes. Phonon frequencies for such modes increase with the in-plane lattice parameter since atoms in the layer upon stretching will be less free to move in the Z direction. This is similar to the behavior of a string, which, when it is stretched, will have vibrations of smaller amplitude and higher frequency. This phenomenon, named membrane effect, was predicted by Lifshitz in 1952. Mechanical, the carbon-carbon bond length in graphene is about 0.142 nanometers. Graphene sheets stack to form graphite with an interplanar spacing of 0.335 nm. Graphene is highly impermeable and is highly elastic. Graphene is one of the strongest materials known with a breaking strength over 100 times greater than a hypothetical steel film of the same thickness, with a Young's modulus of 1 atpa. The Nobel announcement illustrated this by saying that a 1 square meter graphene hammock would support a 4 kg cat but would weigh only as much as one of the cat's whiskers, at 0.77 mg. Flat graphene sheets are unstable with respect to scrolling, that is bending into a cylindrical shape, which is its lower energy state. The spring constant of suspended graphene sheets has been measured using an atomic force microscope. Graphene sheets, held together by van der Waals forces, were suspended over CO2 cavities where an AFM tip was probed to test its mechanical properties. Its spring constant was in the range 1 Euro 5 newtons per meter and the stiffness was 0.5 atpa, which differs from that of bulk graphite. These high values make graphene very strong and rigid. These intrinsic properties could lead to using graphene for NEMS applications such as pressure sensors and resonators. As is true of all materials, regions of graphene are subject to thermal and quantum fluctuations in relative displacement. Although the amplitude of these fluctuations is bounded in 3D structures, the Mermina-Wagner theorem shows that the amplitude of long-wavelength fluctuations grows logarithmically with the scale of a 2D structure, and would therefore be unbounded in structures of infinite size. Local deformation and elastic strain are negligibly affected by this long-range divergence in relative displacement. It is believed that a sufficiently large 2D structure, in the absence of applied lateral tension, will bend and crumple to form a fluctuating 3D structure. Researchers have observed ripples in suspended layers of graphene, and it has been proposed that the ripples are caused by thermal fluctuations in the material. As a consequence of these dynamical deformations, it is debatable whether graphene is truly a 2D structure. Spin transport. Graphene is claimed to be an ideal material for spintronics due to its small spin-orbit interaction and the near absence of nuclear magnetic moments in carbon. Electrical spin current injection and detection has been demonstrated up to room temperature. Spin coherence length above 1 micrometer at room temperature was observed, and control of the spin current polarity with an electrical gate was observed at low temperature. Strong magnetic fields, Graphene's quantum Hall effect in magnetic fields above 10 teslas or so reveals additional interesting features. Additional plateaus of the Hall conductivity at width are observed. Also, the observation of a plateau at in the fractional quantum Hall effect at were reported. These observations would indicate that the fourfold degeneracy of the Landau energy levels is partially or completely lifted. One hypothesis is that the magnetic catalysis of symmetry breaking is responsible for lifting the degeneracy. Forms, nanostripes, graphene nanoribbons, at low temperatures, show spin-polarized metallic edge currents, which also suggests applications in the new field of spintronics. Oxide. Using paper-making techniques on dispersed, oxidized and chemically processed graphite in water, the monolayer flakes form a single sheet and create strong bonds. These sheets, called graphene oxide paper, have a measured tensile modulus of 32 GPa. The chemical property of graphite oxide is related to the functional groups attached to graphene sheets. These can change the polymerization pathway in similar chemical processes. Graphene oxide flakes in polymers display enhanced photoconducting properties. Graphene is normally hydrophobic and impermeable to all gases and liquids. However, when formed into graphene oxide-based capillary membrane, both liquid water and water vapor flow through as quickly as if the membrane was not present. Chemical modification. Soluble fragments of graphene can be prepared in the laboratory through chemical modification of graphite. First, microcrystalline graphite is treated with an acidic mixture of sulfuric acid and nitric acid. A series of oxidation and exfoliation steps produce small graphene plates with carboxyl groups at their edges. These are converted to acid chloride groups by treatment with thionyl chloride. Next, they are converted to the corresponding graphene amide via treatment with octadsilamine. The resulting material is soluble in tetrahydrofuran, tetrachloromethane and dichloroethane. Refluxing single-layer graphene oxide in solvents leads to size reduction and folding of individual sheets as well as loss of carboxylic group functionality, by up to 20%, indicating thermal instabilities of SlGO sheets dependent on their preparation methodology. When using thionyl chloride, acyl chloride groups result, which can then form aliphatic and aromatic amides with a reactivity conversion of around 70–80%. Hydrazine reflux is commonly used for reducing SlGO to SlG(R), but titrations show that only around 20–30% of the carboxylic groups are lost, leaving a significant number available for chemical attachment. Analysis of SlG(R) generated by this route reveals that the system is unstable, and using a room temperature stirring with HCl leads to around 60% loss of COOH functionality. Room temperature treatment of SlGO with carbodiamides leads to the collapse of the individual sheets into star-like clusters that exhibited poor subsequent reactivity with amines. It is apparent that conventional chemical treatment of carboxylic groups on SlGO generates morphological changes of individual sheets that leads to a reduction in chemical reactivity, which may potentially limit their use in composite synthesis. Therefore, chemical reactions types have been explored. SlGO has also been grafted with polyolilumine, cross-linked through epoxy groups. When filtered into graphene oxide paper, these composites exhibit increased stiffness and strength relative to unmodified graphene oxide paper. Full hydrogenation from both sides of graphene sheet results in graphene, but partial hydrogenation leads to hydrogenated graphene. Similarly, both-side fluorination of graphene leads to fluorographene, while partial fluorination provides fluorinated graphene. Ligand/complex. Graphene can be a huge ligand to coordinate metals and metal ions by introducing functional groups. Structures of graphene ligands are similar to, for example, metal porphyrin complex, metal phthalocyanine complex, and metal phenanthroline complex. Copper and nickel ions has been coordinated with graphene ligands. Bilayer. Bilayer graphene displays the anomalous quantum Hall effect, a tunable band gap and potential for excitonic condensation making it a promising candidate for optoelectronic and nanoelectronic applications. Bilayer graphene typically can be found either in twisted configurations where the two layers are rotated relative to each other, or graphitic Bernal stacked configurations where half the atoms in one layer lie atop half the atoms in the other. Stacking order and orientation govern the optical and electronic properties of bilayer graphene. One way to synthesize bilayer graphene is via chemical vapor deposition, which can produce large bilayer regions that almost exclusively conform to a Bernal stack geometry. Fiber. In 2011, Xinming Li and Hongwei Tsu from Tsinghua University reported a novel yet simple approach to fabricate graphene fibers from chemical vapor deposition grown graphene films. The method was scalable and controllable, delivering tunable morphology and pore structure by controlling the evaporation of solvents with suitable surface tension. Flexible all-solid-state supercapacitors based on this graphene fibers were demonstrated in 2013. 3D. In 2013, a three-dimensional honeycomb of hexagonally arranged carbon was termed 3D graphene, although self-supporting 3D graphene has not yet been produced. Reinforced. Graphene reinforced with embedded carbon nanotube reinforcing bars is easier to manipulate, while improving the electrical and mechanical qualities of both materials. Functionalized single or multi-walled carbon nanotubes are spin-coated on copper foils and then heated and cooled, using the nanotubes themselves as the carbon source. Under heating, the functional carbon groups decompose into graphene, while the nanotubes partially split and form in plane covalent bonds with the graphene, adding strength. I stacking domains add more strength. The nanotubes can overlap, making the material a better conductor than standard CVD-grown graphene. The nanotubes effectively bridge the grain boundaries found in conventional graphene. The technique eliminates the traces of substrate on which later separated sheets were deposited using epitaxy. Stacks of a few layers have been proposed as a cost-effective and physically flexible replacement for indium tin oxide used in displays and photovoltaic cells. Production techniques. Isolated 2D crystals cannot be grown via chemical synthesis beyond small sizes even in principle, because the rapid growth of phonon density with increasing lateral size forces 2D crystallites to bend into the third dimension. However, other routes to 2D materials exist. Fundamental forces place seemingly insurmountable barriers in the way of creating 2D crystals. The nascent 2D crystallites try to minimize their surface energy and inevitably morph into one of the rich variety of stable 3D structures that occur in soot. But there is a way around the problem. Interactions with 3D structures stabilize 2D crystals during growth. So one can make 2D crystals sandwiched between or placed on top of the atomic planes of a bulk crystal. In that respect, graphene already exists within graphite. One can then hope to fool nature and extract single-atom-thick crystallites at a low enough temperature that they remain in the quenched state prescribed by the original higher temperature 3D growth. The two basic approaches to producing graphene are to cleave multi-layer graphite into single layers or to grow it epitaxially by depositing one layer of carbon onto another material. The former was developed first, using adhesive tape to peel monolayers away. In either case, the graphite must then be bonded to some substrate to retain its 2D shape. Other techniques have also been developed. Exfoliation. As of 2014, exfoliation produced graphene with the lowest number of defects and highest electron mobility. Adhesive tape. Cleavage is also known as exfoliation. Achieving single layers typically requires multiple exfoliation steps, each producing a slice with fewer layers, until only one remains. Geim and Novosol used adhesive tape to split their graphene. After exfoliation, the flakes are deposited on a silicon wafer using dry deposition. Crystallites larger than 1 mm and visible to the naked eye can be obtained with a technique. It is often referred to as a Scotch tape, or drawing method. The latter name appeared because the dry deposition resembles drawing with a piece of graphite. Wedge-based mechanical exfoliation. Another controlled technique to produce few layers of graphene uses a wedge type of tool to address difficulties of the adhesive tape method. In this method, a sharp single crystal diamond wedge penetrates onto the graphite source to exfoliate layers. This method uses highly ordered pyrolytic graphite as the starting material. The experiments were supported by molecular dynamic simulations. Reduction of graphite oxide. Graphite oxide reduction was probably the first method of graphene synthesis. P. Boreham reported producing monolayer flakes of reduced graphene oxide in 1962. G. acknowledged Boreham's contribution. Rapid heating of graphite oxide and exfoliation yields highly dispersed carbon powder with a few % of graphene flakes. Reduction of graphite oxide monolayer films, for example by hydrazine with annealing in argon hydrogen, was reported to yield graphene films. However, the quality is lower compared to Scotch tape graphene, due to incomplete removal of functional groups. Furthermore, the oxidation protocol introduces permanent defects due to over-oxidation. The oxidation protocol was enhanced to yield graphene oxide with an almost intact carbon framework that allows efficient removal of functional groups. The measured charge carrier mobility exceeded 1,000 cm versus. Spectroscopic analysis of reduced graphene oxide has been conducted. Sonication, applying a layer of graphite oxide film to a DVD and burning it in a DVD writer produced a thin graphene film with high electrical conductivity and specific surface area that was highly resistant and malleable. Solvent-aided, dispersing graphite in a proper liquid medium can produce graphene by sonication. Graphene is separated from graphite by centrifugation, producing graphene concentrations initially up to 0.01 mg per milliliter in N-methylpyrrolidone and later to 2.1 mg per milliliter in NMP. Using a suitable ionic liquid as the dispersing liquid medium produced concentrations of 5.33 mg per milliliter. Graphene concentration produced by this method is very low, because nothing prevents the sheets from restacking due to van der Waals forces. The maximum concentrations achieved are the points at which the van der Waals forces overcome the interactive forces between the graphene sheets and the solvent molecules. Solvent surfactant aided, adding a surfactant to a solvent prior to sonication prevents restacking by adsorbing to the graphene's surface. This produces a higher graphene concentration, but removing the surfactant requires chemical treatments. Immiscible liquids, sonicating graphite at the interface of two immiscible liquids, most notably heptane and water, producing macro-scale graphene films. The graphene sheets are adsorbed to the high-energy interface between the heptane and the water, where they are kept from restacking. The graphene remains at the interface even when exposed to force in excess of 300,000 G. The solvents may then be evaporated. The sheets are up to 95% transparent and conductive. Epitaxy. Epitaxy refers to the deposition of a crystalline overlay on a crystalline substrate, where there is registry between the two. In some cases epitaxial graphene layers are coupled to surfaces weakly enough to retain the two-dimensional electronic band structure of isolated graphene. An example of weakly coupled epitaxial graphene is the one grown on SiC. Graphene monolayers grown on silicon carbide and iridium are weakly coupled to these substrates, and the graphene-Euro substrate interaction can be further passivated. Silicon carbide. Heating silicon carbide to high temperatures under low pressures reduces it to graphene. This process produces epitaxial graphene with dimensions dependent upon the size of the wafer. The face of the SiC used for graphene formation, silicon or carbon terminated, highly influences the thickness, mobility and carrier density of the resulting graphene. Graphene's electronic band structure was first visualized in this material. Weak anti-localization is observed in this material, but not in exfoliated graphene produced by the drawing method. Large, temperature-independent mobilities approach those in exfoliated graphene placed on silicon oxide, but lower than mobilities in suspended graphene produced by the drawing method. Even without transfer, graphene on SiC exhibits massless Dirac fermions. The weak van der Waals force that provides the cohesion of multi-layer graphene stacks does not always affect the electronic properties of the individual layers. That is, while the electronic properties of certain multi-layered epitaxial graphenes are identical to that of a single layer, in other cases the properties are affected, as they are in bulk graphite. This effect is well understood theoretically and is related to the symmetry of the interlayer interactions. Epitaxy or graphene on SiC can be patterned using standard microelectronics methods. A band gap can be created and tuned by laser irradiation. Metal substrates. The atomic structure of a metal substrate can seed the growth of graphene. Ruthenium. Graphene grown on ruthenium does not typically produce uniform layer thickness. Bonding between the bottom graphene layer and the substrate may affect layer properties. Iridium. Graphene grown on iridium is very weakly bonded, uniform in thickness and can be highly ordered. As on many other substrates, graphene on iridium is slightly rippled. Due to the long-range order of these ripples, minor gaps in the electronic band structure become visible. Nickel. High-quality sheets of full-layer graphene exceeding 1 cm2 in area have been synthesized via chemical vapor deposition on thin nickel films using multiple techniques. The growth of graphene on nickel films through chemical vapor deposition occurs in a few steps. First, the thin nickel film is exposed to argon gas at 900, 1000 I½ degrees Celsius. Methane is then mixed in the gas, and the carbon from the methane is absorbed into the nickel film. The nickel-carbon solution is then cooled down in argon gas. During the cooling process, the carbon diffuses out of the nickel to form graphene films. Another used temperatures compatible with conventional CMOS processing, using a nickel-based alloy with gold as catalyst. This process dissolves carbon atoms inside a transition metal melt at a certain temperature and then precipitates the dissolved carbon at lower temperatures as single-layer graphene. The metal is first melted in contact with a carbon source, possibly a graphite crucible inside which the melt is carried out, or graphite powder chunks that are placed in the melt. Keeping the melt in contact with the carbon at a specific temperature dissolves the carbon atoms, saturating the melt based on the metal-carbon binary phase diagram. Lowering the temperature decreases carbon solubility and the excess carbon precipitates atop the melt. The floating layer can be either skinned or frozen for later removal. Using different morphology, including thick graphite, full-layer graphene and SLG were observed on metal substrate. Raman spectroscopy proved that SLG had grown on nickel substrate. The SLG Raman spectrum featured no d and r² band, indicating its pristine nature. Since nickel is not Raman active, direct Raman spectroscopy of graphene layers on top of the nickel is achievable. Another approach covered a sheet of silicon dioxide glass on one side with a nickel film. Graphene deposited via chemical vapor deposition formed into layers on both sides of the film, one on the exposed top side, and one on the underside, sandwiched between nickel and glass. Peeling the nickel and the top layer of graphene left intervening layer of graphene behind on the glass. While the top graphene layer could be harvested from the foil as in earlier methods, the bottom layer was already in place on the glass. The quality and purity of the attached layer was not assessed. Copper. An improvement of this technique employs copper foil. At very low pressure, the growth of graphene automatically stops after a single graphene layer forms. Arbitrarily large films can be created. The single-layer growth is also due to the low concentration of carbon in methane. Larger hydrocarbons such as ethane and propane produce bilayer coatings. Atmospheric pressure CVD growth produces multi-layer graphene on copper. Sodium ethoxide pyrolysis, gram quantities of graphene were produced by the reduction of ethanol by sodium metal, followed by pyrolysis of the ethoxide product and washing with water to remove sodium salts. Silicon-hydrogen, a normal silicon wafer coated with a layer of germanium dipped in dilute hydrofluoric acid strips the naturally forming germanium oxide groups, creating hydrogen-terminated germanium. Chemical vapor deposition deposits a layer of graphene on top. The graphene can be peeled from the wafer using a dry process and is then ready for use. The wafer can be reused. The graphene is wrinkle-free, high quality and low in defects. Nanotube slicing, graphene can be created by cutting open carbon nanotubes. In one such method, multi-walled carbon nanotubes are cut open in solution by action of potassium permanganate and sulfuric acid. In another method, graphene nanoribbons were produced by plasma etching of nanotubes partly embedded in a polymer film. Carbon dioxide reduction, a highly exothermic reaction, combusts magnesium in an oxidation reduction reaction with carbon dioxide, producing a variety of carbon nanoparticles including graphene and fullerenes. The carbon dioxide reactant may be either solid or gaseous. The products of this reaction are carbon and magnesium oxide. U.S. Patent 8,377,408A was issued for this process. Spin coating. In 2014, carbon nanotube reinforced graphene was made via spin coating and annealing functionalized carbon nanotubes. The resulting material was stronger, flexible and more conductive than conventional graphene. Supersonic spray. Supersonic acceleration of droplets through a laval nozzle was used to deposit small droplets of reduced graphene oxide in suspension on a substrate. The droplets disperse evenly, evaporate rapidly and display reduced flake aggregations. In addition, the topological defects, Stone-Wales defect and C2 vacancies, originally in the flakes disappeared. The result was a higher quality graphene layer. The energy of the impact stretches the graphene and rearranges its carbon atoms into flawless hexagonal graphene with no need for post-treatment. Applications. While as of 2014, graphene is not used in commercial applications, many have been proposed and/or are under development, in areas including electronics, biological engineering, filtration, lightweight strong composite materials, photovoltaics and energy storage. Graphene is produced as a powder and as a dispersion in a polymer matrix, or adhesive, elastomer, oil and aqueous and non-aqueous solutions. The dispersion is stated by the manufacturer to be suitable for advanced composites, paints and coatings, lubricants, oils and functional fluids, capacitors and batteries, thermal management applications, display materials and packaging, inks and 3D printers, unregistered trademark materials, and barriers and films. See also. References. Sources: Jim, A.K. Novoselov, K.S. The Rise of Graphene. Nature Materials 6, 183 €91. Bibcode, 2007 NatMar. 6183 GDOI, 10.1038/MAT1849. PMIDA 17,330,084. External links: Graphene at the periodic table of videos. Most of graphene papers published by André Geim's group are downloadable here. Is graphene the new silicon? National Science Foundation, March 27, 2008. Band structure of graphene. Retrieved August 15, 2009. Graphene portal with daily news and resources. Castro Neto, Antonio H. Pauling's Dreams for Graphene. Perez, NMR. Ribeiro, R.M. Focus on Graphene. New Journal of Physics 11, 095002. Bibcode, 2009 NJPH. 11i5002 PDOI, 10.108811095002. Online short course, Colloquium on Graphene Physics and Devices, list of authority articles on graphene theme, short video explanation, what is graphene? Short video Graphene and the Carbon Revolution, scientists find simple way to produce graphene, graphene technology moves closer, graphene, patent surge reveals global race, what graphene offers for future electronic devices by Linda Ray, graphene shows promise, researchers are looking for new materials that can take over where silicon will leave off, defects improve graphene conductivity, IOP Science Graphene articles, PDF. Engineering controls for nanoscale graphene platelets during manufacturing and handling processes, Graphene, September 15, 2010, BBC radio program Discovery.